So for Bernoulli's equations, okay, so for a Bernoulli equation is an equation of the form, again, we have a y prime plus some function of x multiplying the dependent variable y equals some function of x very similar to that of the linear function. However, it's multiplied by y to the n power, which is what makes it a non-linear differential equation. All right? We discussed a couple of different cases. That is, if n equals to 0, we just get y prime plus py equals to q, which is really a linear first order equation. And if n equals to 1, that becomes a separable equation, as we did at the very end of the last lecture. Well, so what's the behind the scenes of solving a differential of a Bernoulli equation? Well, here we need to substitute v equals to y to the 1 minus n. Well, what is that? Because we want to turn a nonlinear differential equation into a linear equation. That is, we're going to subtract n from 1, so we end up with just 1. That's the real trick here, all right? And then the derivative and all that, well, we will do for substitution. Okay, so let's have a look at the first example. Solve its Bernoulli's differential equation. Y prime equals 4 over x, y. Wait, what happened here? There we go. Okay, maybe. Let me get rid of this. Okay, there we go. I don't need Wi-Fi. All right, so, no, that's not what I wanted. Bernoulli's. Okay, so, solving this Bernoulli's differential equation, we need to write it in the correct form. That is, we need to have the term containing the y to the first power on the left-hand side of the equation. Okay, that's y prime minus 4 over x, y equals to negative 6x, y squared. All right. Now, notice how it is in the form where we're going to have a look at the y to the n right here. All right. From here, we get that n equals to 2. Okay. So, using the substitution v equals to y to the 1 minus n power, this will be y to the 1 minus 2, which is v equals to y to the negative 1. All right. Now, let me actually highlight this because we're going to get back to that later. All right. Okay. So, let's take the derivative of this. Finding the derivative dv dx, okay. dv dx, that equals negative 1 times y to the negative 2. Okay, I'm going to do this right this time, times dy dx. Okay, and then I'm going to solve for dy dx okay, let me indicate how we do that. By multiplying both sides by negative y squared. Well, negative y squared, yes. All right. So that's going to leave us with, what is that? dy dx equals negative y squared. All right? So let's do the substitution. So I'm going to substitute the y prime, which is our dy dx, with the dv dx, okay? dv dx. So this becomes right here, okay, let me highlight this. Oh, oops, that's not a highlighter. Okay, so this right here is going to go in the place of here, the y prime, okay? So this will be negative y squared dv dx plus, or rather minus 4 over x y equals to negative 6x y squared. All right? So what are we going to do here? I'm going to divide both sides of the differential equation by y squared. Right? And that's actually in a way to kill this y squared that makes the differential equation a nonlinear one, right? because that's what we want. We don't want a non-linear term. However, there's something weird that's going to happen, like, okay, that's a negative dy. Well, actually, you know what? Let me divide by negative, because I also want to kill all the negatives as well. Okay? So, this is going to be dv dx minus, plus, actually, 4 over x. So y divided by y to the second power, isn't that y to the negative 1? All right? Equals to positive 6x. But our goal here is to turn a nonlinear equation into a linear. Yes, we got to kill that y squared. However, we still have that y to the negative 1, so we're going to go back and forth between linear and nonlinear. Well, remember the substitution here we did for v? Okay, that one goes here. Okay, substitute that into here. Okay, and that's going to be dv dx plus 4 over x v equals to 6x. What do you think of this equation? Does that look like a linear first order equation? Finally, you know how to solve a linear equation. All we need is, what is that? An integrating factor, right? Okay, so let's get that integrating factor. Okay, so number one, let's identify our p of x, which is 4 over x, correct? And our f of x, which is 6x, okay? Okay, so let's see. We need to find mu, which is e to the integral of p of x dx, which is e to the integral of 4 over x dx, which is e to the 4 ln of x. However, we can't cancel this e to the x. Again, first basketball, the coefficient, make it a power of x, all right? And that is e to the ln of x to the 4th, which is x to the 4th. So that's going to be our integrating factor. But again, let's just use the formula for this, okay? So what we're going to do here is, okay, let me go to the other side of the page to keep solving the linear equation. So okay, guys, you know the formula as a y mu equals to the integral of mu f dx. However, right now, when we're solving Bernoulli's equation, our intermediate variable is not y, it's v. So I'm going to replace this y with a v, okay? V mu equals the integral of mu f dx, okay? What's v? Well, that's going to be our dependent variable. What's mu? Times x to the 4th power equals the integral of x to the 4th times 6x dx, and let's just solve this, evaluate this integral, all right? V times x to the 4th equals 6x to the 5th, 6 times the integral of x to the 5th dx, which is vx to the 4th equals to x to the 6th power plus c, all right? So first of all, let's solve for v by dividing both sides by x to the 4th. So v equals to, what is that? Wait, what happened here? Oh, that is x to the 6th plus c divided by x to the 4th. However, this is the solution to the differential equation under the variable v, all right? Our dependent variable is actually y, not v. That's where we're going to go back to, again, that same substitution we set at the beginning right here, all right? Okay, so let's see. So this is the same as saying 1 over y to the negative 1, which is x to the 6th plus c over x to the 4th, okay? And you can do a couple of steps right here. Do you guys agree this is 1 over y? And, or if you raise, well, let me do the 1 over y equals to x to the 6th plus c over x to the 4th. Well, if we flip both sides of the equation, that gives us the general solution, y equals to x to the fourth power divided by x to the sixth plus c. And that is our final answer. All right? That's our final answer here. Okay. All right, well, let's do another example involving, what's it called, this Bernoulli's equation. Okay, so the next example, which is on the next page, actually it's also the last page of the notes. That's how we're going to wrap up the section. What do we have? dy dx plus 1/3 y equals e to the x, y to the 4th. Well, clearly by looking at the equation, this y to the 4th term makes it a nonlinear equation. What's the pattern again? Okay, so a nonlinear equation becomes linear, which at the same time becomes a separable one. All right? So, okay. So from here, well, actually the equation it's given already in the form for a Bernoulli's equation with n equals to 4. Let's start by doing the substitution, which is v equals to y to the 1 minus n, which is y to the 1 minus 4, which is v equals to y to the negative 3. All right? So that's what we're going to do here for the v. And again, let me highlight it, because we're going to go back to this equality a couple times. Once when we eliminate the nonlinear term, and the second time when we back substitute for v to get the equation or the solution to the equation in terms of v. All right? I mean in terms of y. Okay, so number one, let's find the derivative of this. Okay, so dv dx, that equals negative 3 y to the negative 4, careful, dy dx. All right? Now, one thing to notice when you're doing the substitution and the derivative, we will always get this y to the negative power of the n in the original, because that's what we're going to use to kill that nonlinear factor, right? So if for some reason you get a different number, double check your derivative, double check your work, because it's a good way to assess your work so far. All right? So solving for dy dx, that'll be, okay, dy dx by multiplying both sides by, or actually, okay, let me show the multiplication, because, so I'm going to multiply both sides by y to the 4th over negative 3. Y to the 4th over negative 3. All right? Okay, so this will be dy dx equals to negative 1/3, okay, y to the 4th dv dx. What are we going to do? Okay, let me highlight this with the color I did before. Okay, this will replace the dy dx term. All right, or here. Okay, so we're going to go back to the differential equation. So this will be negative 1/3. Okay. So negative 1/3 y to the 4th dv dx, and then what is that? Plus 1/3 y, okay, plus 1/3 y equals to e to the x, y to the 4th. All right. Well, so we have v's, y's, etc. Well, here we want to get rid of the y's to the 4th. So actually, I'm going to multiply both sides by negative 3 over y to the 4th, negative 3 over y to the 4th, okay? That's going to turn the derivative term into a coefficient equal to 1. dv dx plus, okay, what's going to happen here? Negative 3 times a positive 1/3 cancels to get actually a negative. And y divided by y to the 4th, isn't that y to the negative 3? equals to negative 3 e to the x. All right? So yes, we got rid of the y to the n, the y to the 4, but we still have that y to the negative 3, which still makes the equation a non-linear. However, remember this? Remember this, the substitution here? That's actually our v. And now we're going to have an equation in terms of v. Okay? So, dv dx minus v equals negative 3 e to the x. And that's a linear equation under the dependent variable v, and the independent variable is still x. All right? We know how to solve this linear equation. Let's identify our p of x, which is simply negative 1, and our f of x, which is negative 3 e to the x. Okay? So let's find mu, our integrating factor, e to the integral of p dx, or p of x. I'm just going to abbreviate, okay? So that's e to the integral of negative 1 dx, which is e to the negative x, okay? No logarithms, no cancellations. That's our mu this time, all right? Okay, so for the formula, so v mu equals to the integral of mu f dx. Okay, just substitute into the formula to solve the linear equation. Okay, so substitute mu equals to e to the negative x, so that's v e to the negative x equals the integral of e to the negative x times f, which is, what is that? Negative 3 e to the x. Wait, yes. Dx. Do you see what's going to happen here? E to the negative x cancels e to the positive x. And v e to the, oops, make it look like a v e to the negative x equals the integral of negative 3 dx, which is negative 3x plus c. So we're essentially done with the integration and also essentially with the solution to the equation. Let's just solve for v and also find solve for v and back substitute for v. Okay? So I'm going to divide both sides by e to the negative x and this will be v equals negative 3 e to the negative 3x e to the x plus c e to the x. Okay, so I'm also moving the exponential to the numerator with positive exponent. All right. So back substitute for v again. What was v? So our v right here. Remember, what did we substitute for v? Y to the negative 3. Okay, so this is y to the negative 3 equals to negative 3x e to the x plus c e to the x. Well, the rest of the problem is just 1 over y cubed equals to negative 3x e to the x plus c e to the x. Well, you can always think of this, all this madness here. How about, is that divided by 1? Simply flip both sides of the equation to get y cubed equals to 1 over, I'm going to write the positive term first, c e to the x minus 3x e to the x. And then we can get the y by itself by taking the cube root on both sides. All right? So y equals to the cube root of c e to the x minus 3x e to the x in the denominator of 1. All right? And everything under the radical. All right? And that is the solution to the differential equation, a Bernoulli's equation. Okay? That's also the end of the section. Okay?